Equipollent systems are systems um, with different loads but the same behavior. Um, and it turns out that with rigid bodies, there are a lot of times that replacing one set of loads with another set of loads makes your calculations easier. And so with rigid bodies, you can always replace a set of loads with an equipollent set of loads. So some examples of this are well, the first one is one that we already have been using. I didn't call it an equipollent system, but it's the same. That's what it is. You can replace a force couple with a pure moment. We do that all the time, but two forces that are applied that are equal and opposite are not a moment. It's two forces. We replace it with the pure moment because it makes the calculations easier. Another thing that you can do that we haven't done, and I'm not going to talk about how to do it, but you can do this. You can replace any combination of loads with a force vector at a chosen location that you choose. So a single force vector at a location of your choice and a couple. I don't find that to be usually super useful. It doesn't come up in any calculations really that I do. There was one kind of calculation that I used to do with my work a long time ago where this was a useful thing. And that is that any muscle forces for any joint can be replaced by just a pure joint moment. So a moment like a couple on one body and an equal and opposite couple on the other one. You wouldn't think so, but you can figure that out with this approach. And then the third one is the one I'm going to talk about. You can move any force vector along its line of action. Okay, so this is the one I'm going to talk about for a second. And so what that says is if you have some object and there's a force vector acting on it there, okay? The line of action, and actually I'm going to move this a little bit. The line of action is the line that is parallel to that vector and goes through the point where the force is applied. I think this picture gets that idea across better than words. Okay, so the red is called the line of action. And if it makes the calculation easier, you can move that force vector. Let me name it. So this force vector F anywhere you want along that dotted line. So you can say that force is applied here or here or here. And this is sort of a weird thing, but you can even say that this force is applied to this object here, outside of where the object is a mile away, as long as you stay on that line of action. It's just a mathematical thing, but the math everything will be the same no matter where you move it. And sometimes that makes things a little easier. Let's see. Yeah. So let me just show you an example of this. Yes?
Like I would see in physics, our professor would always have normal force from the center of mass.
Yeah.
But you do it at the center of mass?
Yeah.
Is that?
Well, let's see. Is that physics people don't do a lot of rigid body calculations so they tend to think of, they're more likely to think of everything as a particle, you know, because that's sort of the kind of calculations that they've done their research more and stuff. I think that's why. And so they kind of tend to think of everything as happening at the center of mass of an object. But when you're doing rigid body stuff, where a force acts actually is important, you know? So I think that's really more what that is. Physics people just tend to think of objects as particles more than mechanical engineers and stuff do. Okay, so let me show you how this works. Oh, by the way, I said that this only works with rigid bodies. This doesn't work with deformable bodies. So if you're not considering an object as rigid, then you can't make this substitution. Let me show you, give you sort of an idea of why that is. Doesn't work with deformable bodies. Deformable. So say that you have an object. So you start with this blob of, you know, silly putty. If you apply a force to it up here, it would do that. If you move that force along its line of action, it would do this. Yeah, so you can only make this substitution and have the calculations be the same when you're treating things as rigid bodies. You know, these are not the same. Yes?
Well, like if the line of action is more of like, what's it called? Decant of a circle or
Tangent?
not tangent, but like more like barely on the object,
Yeah.
you know what I mean? What could it create different moments?
Well, actually, that's exactly why it does work for rigid bodies, is because it doesn't, because the moments are the same. Um, so it's exactly, you know, if you think of a moment, so we do it with cross products, but if you think of a moment as like a force times its perpendicular moment arm, the idea of this is that you keep all the moment arms the same. So that's really, that's why it does work. Okay, so let me do an example. So let's say there's this guy exercising. I've never seen anyone do this kind of exercise, but it could be, I don't know. I'm not a big exerciser. And this is against the wall. Okay, so let's say that we know that there's a friction contact down here. And let's say that the center of mass is 1/2 meter from where the feet make contact horizontally. So here's the center of mass. By the way, treating gravity, we'll get into distributed loads pretty soon, but treating weight like it acts at a single point at your center of mass is an equipollent system. Gravity doesn't really just doesn't calculate where your center of mass is and apply a force there. What it does is it applies a little force all over your body, and calculating the center of mass and applying the whole thing like it acts at the center of mass is just an equipollent system. Okay. Okay, so this distance is 1/2 meter. And then this distance, where the roller is 0.8 meters. And we want to know what are the reactions. Well, if you draw a free body diagram, okay, so there's the outline. The weight acts here. Did I give his weight? 80, it's supposed to be a mass of 80 kilograms. So 80 times 9.81 is 784.8. Is that right? 78. I think that's right. And then here we have a reaction force RA, and then here at the roller we have a force RB with a known direction. And notice that with the dimensions that I gave, we know the horizontal distance between these two, but I didn't give a height of the center of mass. Okay. And we know the vertical distance between the floor and the RB, but I didn't give a horizontal distance for when that force is applied. So really, like, if we're using the definition of the row vector, we can't calculate those row vectors. You know what I mean? We don't have a vertical component for this one, and we don't have a horizontal component for this. But thinking about it in terms of moving them along their line of action, you realize that those wouldn't come into it anyways. So we can move this weight force along its line of action down to the ground. We can move this horizontal force over here horizontally until it's, right above that, and it won't change anything. Okay. So here we don't know the height. And here we don't know the horizontal position. So let's fill out a table for rho, force, moment. So first for the force RA, and I'm going to make this the about point. It's acting at the about point, so the rho vector is 0. The force is RAX, RAY, so the moment is 0. And now I'll go to the weight force. Okay, so the horizontal component of the rho vector is positive 0.5. The vertical component we don't know, but we know that it's not going to matter because this is the line of action. Okay, so I'm just going to put that in as 0. We know it won't hurt anything. The force vector is 0, negative 784.8. And multiply those two together and you get negative 39.24. 392.4. And then this one, that's the line of action of this RB. We know the vertical component is positive 0.8. We don't know the horizontal component, but that can be anything, so I'll just make it 0. And then the force vector is negative RB 0. And so you get 0.8 RB. And you can go through the calculations. You get that R is equal to 490.5, 784.8, and RB is 490.5. And mathematically, let me show you why this works. What if the approach that we took was we just gave those variable names to things that we don't know. So we said that for the rho vector for the weight force, we had 0.5 for x, and we just call this some unknown a or something. Okay. And now take the cross product. You have 0.5 times this minus a times 0. It goes away. Okay. So this gives the same cross product as if we do that. That's how this line of action thing works. And same thing for this. That rho vector from the about point to where that roller hits the ball. So we don't know the vertical distance is 0.8. We don't know the horizontal distance, so let's call that B, some unknown. So you have a B here. Now take the cross product, B times 0 minus that, and you get the same thing, whether it was there or not. Okay, so sometimes that's useful, and even if you know those values, thinking about it that way can sometimes just make the calculations a little quicker.